for today's class, I think we can move to the vector fields for work. Okay. Although maybe we don't really have much content before in work, but I hope I can cover the today's class for the work using the vector fields and line integrals. Okay. So recall. Let me write first. Recall that work is basically an integrations of our functions. Or if you learn by physics, it's actually force and you have some distance, right? And in terms of vector, so this is one, and second, in terms of vector, we found that the work done by constant force, so let me write work done by constant F in moving an object from P to, let's say, Q to another point in space, we can write work as F dot D. Okay? So it's force and the displacement vector, which is D, is a vector defined from P to Q. Okay? Now suppose that we have a vector F. So suppose we have F we define in three-dimensional vector. So P, Q, R. So suppose that F is continuous vector field. Okay, of course in 3 dimensions or on the domain of 3 dimensions. So this F could be like gravitational field or electric force field. So we want to measure or we want to compute the work. So let me write here. So our goal is compute the work done by this F along smooth curve. So now it's not moving an object from P to Q, not only that, but we have a definition of a curve. Suppose the curve is a curve C. If we could see the picture. So we have a vector field, blue directions arrow, and we have a smooth curve C. So we want to find, or we want to compute the work on this done by this vector along this curve. So we are going to focus now on this curve C and taking some point by point along the curve, meaning we are going to observe the arc length. We are going to observe the arc length, and then we also see some other variable here, which this is the tangent vector. Do you remember? So let me write some of the notes here. So here we are going to have so divide the curve C into subarcs. Let's say subarcs pi minus 1 pi. Okay. So this the smallest, we define that is the smallest arc length on the curve C, or the subarcs. Okay. With length delta S. So meaning this is going to be dividing the interval from A to B into subintervals. And then we choose sample point pi. So choose pi asterisk as mentioned in the picture as our sample point. Correspond to sample parameter to ti asterisk, just a sample point. It can be anywhere along the curve. Okay? And if the delta S is small, then I can write approximately as the particle move along the curve, it is move along the curve to the directions, to the in the directions of the t at the ti asterisk. The t is unit tangent vector. Unit tangent vector at the pi asterisk. So mathematically we can write so work done by F, then F at this sample point XYZ dot the delta S. This is supposed to be the D, and we define this as delta S T, and then equal, we can just rewrite this in terms of this is the same thing, but here we have T, because this is the vector. So the T is vector, F is vector. We can write this in front, and then we factor the delta S. The delta S is a scalar. Okay. And so we can write this as the sum and we can also exchange the t using the same xyz. And then delta s I. Right, t xyz is unit tangent vector at point x, y, z on C. And of course, this sum we can write as a Riemann definitions for the integrations. Okay, so Riemann definition or Riemann sum definition. Okay. So based on the Riemann definitions, then we can write that the work is equal line integral on the curve C, the f at the point xyz, and then ds. Or simply you can write f dot t ds. So this means that the work is line integral with respect to the arc length let me write completely. So the arc length of the tangential component of the force. Okay. So from the Riemann, we can write using the integral, the line integral. Okay. And the unit tangent vector, if you remember, is actually the r prime divided by its magnitude of the factors, right? If you remember. Let me write some notes here. What is the t? Okay. So if, let me write here, okay? Just a quick notes here. So if the curve C is given by the vector equation R, and we have each one of them parametric definitions. Okay, so suppose that this is the vector equations. Then the t is actually r prime t divided with its magnitude value. So using these definitions, we can write the work from A to B okay, and then multiply with r prime t dt. So this is from the AB from the beginning here, okay? And then we trying to compute using the respect of t, and then we can write the work as f r rt dot r prime t dt. Okay. So this is equal with the line integral f dr that we defined previously. So we can write this actually as the integrations or the line integral for f dot dr. Okay. And this is basically becomes our definitions now. So the definition for this work, so if you have f, which is a vector field continuous defined on a curve, smooth curve C, and you have a vector function r of t, where t is from A to B, then the line integral, okay, of f along C is basically equal to line integral f dot dr. And basically what is f dot dr is basically same thing as this f dot unit eigenvector yes. Or if you want to split up becomes the using the vector or the r, you can have the same here, f r of t r prime. And basically, to make sure that we are in line with the definition from the calculus and also from vectors, if you see if we have r of t, okay, if we take d dt of this, we get the dr dt, right? So basically, dr, we could also rewrite directly as this. So I think it's easily to see that the dr here is actually r prime dt, right? Just from the chain rule, differentials is actually the same thing. Okay? And basically this f, we just put in the r or the parametric into the vector fields f. So the f r of t, this is basically just abbreviations or simplification from the parametric. Okay. The process will be very comprehensive, not that complicated. So as long as you go using this definitions, okay, you know the parameter, then I think all the components are available to be computed. Okay. Anyway, next week, I hope everyone get into the class, and I'm still not sure whether there will be a photographer to take some photo of this class, but I'm not sure. They said next week on this class. Okay, but make sure just casually come to the class. Okay, but be aware that you will be taking a photograph, and maybe I will ask something and you need to maybe active a little bit. Okay. Let me give you just a couple examples on this. after this page. Okay. We're going to see some examples. But basically this is the idea. This is the idea. Actually, you can I think start from here by definition, and then we can also write this in terms of R. So R, we put R inside the F, and then P, we can use the definitions, and we start using that, and we get this idea. But to make the conclusion easier to be to comprehend, we can just take the chain rule here from the R, and we know that the R will be R prime T, and the F basically we put inside the R in the vector function. Okay, let me give you examples. So first is this. So we have a vector field F. So we have a vector field which is just a two-dimension vectors, and then we have the R, the vector positions for the curve, basically cosine t at the x-axis and sine t at the y-axis, and you have the parameters. So we have everything. So you can just put everything into the equations, and basically this is the example for the picture. So the blue is the vector fields, and the red is our curve. Okay. So we want to move along this curve and compute the work. Okay. Compute the work done by the vector fields. Okay. So we can write the first. Maybe we write the f of RT, which is we take the cosine t and exchange to the x, right? So x is going to be substituted by the cosine t. So this will be cosine squared t for the x-axis, and then minus, it's actually xy. So cosine t sine t. And then the r prime t, we take the derivative. Okay. And then the work will be line integral f dr, or we can directly use the parameter 0 to pi over 2, the a and b, and basically just write all the terms. This will be dot r prime t dt. So everything put inside the we take the dot product for this particular functions. The dot product, if you don't remember, so you have a let's say vector. You can write like this. So you have negative cosine squared t sine t, right? Let me write here. This is 0 pi over 2 sine t, and then minus cosine t. Cosine t will be cosine squared t sine t. So minus cosine squared t sine t, right? And then it's become a scalar, right? We can scalar the dot product. We add this two. Then we have negative 2. And then basically you can use substitution method, and then you get that this will be 2 cosine cube t over 3. This will be from 0 to pi over 2, which is, it will be cosine 0. It's negative 2 over 3, right? So 0 minus 2 over 3, right? Okay. You can use the substitution method, and you get this result. Okay, the second example is you have this. So you have the vector fields f, 3 dimensions ijk, and then you have the curve C defined by these parametric equations. So first, maybe we can write the R. It's basically, let me just write with these symbols, t squared, t cubed. This is what we call the twisted cubic, okay? The twisted cubic. And R prime becomes 1, 2t, and 3t squared, right? And so the fr of t, using the RTT t squared, so this will be t and t squared become t cubed I plus yz. Yz is t5. And then plus zx, it's 4. Okay, so that's FRT. And then the line integral. Now if you look at how it looks like the curve is the red color. Okay, and all the directions for each factor fields here, it goes by descripting by this number. So this is when t is 1, when t is 3 over 4, 3 is 1 over 2, because t is from 0 to 1. Just to give you some idea on what kind of vector fields we have in within the system. So anyway, the line integrals we can write. So f dot dr. So this will be from 0 to 1, and then FRT dot the R prime t, and then dt. I think I will write this using that. So I will use the dot product. So t cube, and 1 is t cube. So t cube plus the y-axis become t5 and 2t, so 2t6. And then t4 and 3t squared, it's become 3t with power of 6, or I will combine these two, becomes 5t with power of 6. and then dt. And basically this is t with power of 4 this is 1 over 4 plus 5 over 7 27, right? Okay, I think very clear. I mean, simple equations. What you need to do is focusing on the vector functions, focusing on the work that is f dot dr. So from these two examples, we could see that, let me just write some conclusions. We can write, we can have, so note connection between line integrals of vector fields and line integrals of scalar fields. So suppose vector field f is on this domain in 3 dimensions. The vector field is given in component form by equation f equal pi plus qj plus rq. Then using the f dot dr line integral, we have this is actually equal to this, right? This is from our examples and from our works done. So if the f could be written as the pqr using the each axis, then this will be p, q. So basically we change all the f with the pqr. This will be dot. By the r prime will be the x prime t. Let me move to the left a little bit. Plus oh, I forgot the ijk, sorry. This is j, this is k, and then dt. Okay, so basically we are going to multiply each one of them. So this will be a little bit long. So p of xt, yt, zt, okay, and then multiply with the x prime t, and plus q okay, and then multiply with the y prime t plus r at this parametric, and multiply with the z prime t. Okay, I need more space. and then close bracket dt. So this last integral is precisely the line integral that we have before. Oh, I think I haven't wrote. So this is, let me write here, just a note. I forgot to write this for you. Let me write that this is basically the line integral in space. So we can write in terms of p x y z dx plus q x y z dy plus r x y z dz. Okay. So basically we can write the f dot dr using this p dx, q dy, and r dz, okay? Which is basically, that is the line integral in space, where the f is pi, qj, and rk. So if we have, for example, y dx plus z dy plus x dz, we can say that if the f, based on this structure, we can write as yi plus zj plus xk. And then finally, we can write the line integrals f dot dr as line integral p dx. Wait. Different. Okay, just this. So basically, we can write this f dot dr using f is y, z, x. Okay. And for two-dimension vector, we can also write the f dot dr, but we are going to limit the axis only x and y. The f is so basically, if you have the line integral and it has this integral in space or plane, then if you want to find the works and you have the curve, the factor of the curve, the c, then you can use the f and then dot the r or r prime, and then you get the result. Sometimes maybe it is asking directly the equations, and then it's give you the curve. So that means that you need to define what will be your vector fields. What will be your vector fields? And I think it's quite clear. We're just going to see all the elements here, x, y, z, dx, dy, dz, and it will be perfectly in line with the axis, all the axes. Okay, I think that will be the end of our lecture today.